This is the start of our Unit 7, Forces in Motion. Just a reminder, there are lots of videos, separate links. This page specifically, there's a good one on Newton in space. But as you see, as we go along on the different slides, you'll see with the little asterisk, remember, those are the ones that you can click on and get a video or more information. And we highly advise that you take some time and click through those and watch some of those videos, especially if you are struggling between the difference in these different Newton laws. But today we are focusing on Newton's first law, which is the law of inertia. So this is where objects will continue in the same motion unless acted on by unbalanced forces. So they will stay stopped or at the same speed in the same direction.
And while that's going to be the focus of this lecture, Newton also has two other laws, his second and third law that we'll be focusing on in subsequent lectures. Newton's second law will be dealing with a mathematical equation that shows the relationship between acceleration, the force that's applied, and the mass of the object. And so we'll see the relationship between those three quantities. And then lastly, we'll take a look in our last lecture at Newton's third law, which deals with action and reaction forces. In other words, all objects that have a force acting upon them are going to exert a reaction force. And we will see some examples and some evidence of this and see how especially Newton's third law is often used in our space programs to be able to send missions and satellites and probes and things like that into space. And utilize a lot less fuel.
All right, so taking a look at the first law, which is the law of inertia. This is when objects tend to keep doing what they are doing until they are acted on by an unbalanced force. So that is what we call inertia. That is important vocabulary information for you. So inertia is the property of an object to resist change in motion. Okay, an object with a lot of inertia takes a lot of force to stop or start that motion. An amount of inertia an object has depends on its mass. So the more mass an object has, the more inertia it has.
So make sure you've highlighted a couple of those words and phrases in this case emphasize. So first of all, the idea of inertia. Inertia is a property. So the color of my hair, right? Color is a property. The length of my hair, length is a property, right? Size is a property. Mass, how much mass my body has, is a property. Inertia is a property too. So we can use this to describe a specific object. And inertia is related to its mass, all right? We're going to show you a little clip here, hopefully, from Indiana Jones and the Raiders of the Lost Ark. And as you see this, let me see if I can, there we go. You can see here, Indy looks a little concerned, a little bit, because there's a giant boulder rolling after him, right? So there goes our Indiana Jones, the great Harrison Ford there. Good. So we have a little Indiana Jones there running from that giant boulder, right? And you saw his face. He was really concerned, okay? That boulder has a lot of inertia, all right? Why? Because it has a significantly large amount of mass. Would Indiana Jones be as concerned if that boulder was replaced with a golf ball? Hopefully, your answer is no. You would not be as concerned, right? Because that golf ball has a significantly less amount of mass, and therefore it has a significantly less amount of inertia. In other words, the bowling ball is going to require a significant amount of force to slow it down. And Indiana Jones is not going to be able to turn around and put his hand out and stop, or his foot out and stop that boulder, right? More mass in the boulder, Indy's got to run. If it was a golf ball, however, the inertia of that golf ball would be much, much less, right? It doesn't take a lot of force to stop a golf ball, all right? Not nearly as much as it would take to stop the boulder. right? So Indiana Jones, if he turns around and sees a golf ball rolling down that not too steep hill at him, he can turn around, put his foot out, and stop that golf ball with very little problem, okay? So that's one example of inertia. The second example we often talk about is when we're driving or riding around in cars or on the bus, right, or on a train. And when that car or bus or truck or train stops, right, when it slams on, the driver slams on the brakes or slows the vehicle down, all right, you tend to move forward. Think about that. Think about when that's happened to you before. When you do that, think about why that is. Why are you continuing to move when the car is being stopped? Think about forces applied. All right. When the person driving hits the brakes are applied to the car. Are the brakes applied to you? Not so much. So the brakes are slowing the car down, but you are in the car that was moving at, let's say, 45 miles an hour. And so when the brakes hit the car, it slows the car down, but you are still moving at 45 miles per hour. So that's why it's really, really important to wear your seatbelt to make sure that you are going to slow down or be stopped in your movement when that car stops, especially when the brakes are being slammed on. Right? So you have two examples there of inertia, of objects that are resisting change in motion, that are continuing to, as Ms. Case started out by saying, do what they're already doing until the forces become unbalanced. All right. And then the object is going to change its motion. All right. The only reason why you stop is because you come into contact with the seatbelt. Hopefully the seatbelt and not the seat in front of you or the windshield or, you know, forbid, the pavement outside the car. All right. Think now, as we transition and Ms. Case moves into talking about some other aspects of Newton's first law, think about another example of something exhibiting its inertia, its resistance to change in motion, right? And add that to your notes that you've already taken for this slide.
All right, so what is force? The definition and our units here. So forces are pushes or pulls that have the ability to change the motion of an object. Okay, so forces have direction, is important in determining that motion. Our units for force, so we have metric units is newtons, so your capital N. Okay, this is your preferred unit to use for this. Our English unit is pounds, or lb. And then to convert between these two, you have a conversion factor of 4.448 newtons equals 1 pound. Okay, so if we have to switch between those two units, we are going to need to utilize the dimensional analysis, or DA, which is what we used towards the end there of last semester.
So we are going to do our first of two conversions to practice using our conversion factor for newtons and pounds. Because we need to be able to move between our common unit, which is pounds here, all right, the 120 pounds, and we want to end up in newtons, which is our metric system unit. So we are going to follow our rules of DA. I'm going to draw my lines and my little, ooh, that's a terrible line, but that's okay. Better than what was happening before. And we are going to set that up so that we can put our initial amount and our conversion factor, but I'm going to use text boxes for that. Just so it's a little bit neater. So remembering from last semester, our rules of DA say that we put our starting amount, our 120 pounds, with the unit on the top, and we set that up as a fraction over 1. And remember that 1 typically is not going to have any type of unit. It's just allowing us to put our starting amount of 120 pounds into a fraction form, right? Then we're going to use our conversion factor over here, which is telling us 4.448 newtons is equal to 1 pound. And remember, that's like 1 dozen equals 12 donuts, right? We're using a conversion factor to move between units. According to DA, we need to get rid of the pounds and end up with newtons. In order to do that, we have to put pounds from our conversion factor on the bottom. So I'm going to take that 1 pound for my conversion factor, and I'm going to put that at the bottom. And then I am going to take my 4.448 0.448 newtons and put that on top. All right, and then according to our DA practice, we can cancel out our units we don't need. You know me, I like to circle my unit that I do, and I've gotten to the unit I want, right? I want newtons. So winning at life. Now I'm going to finish up and do my math. Remember, our last step of DA says to multiply across the top, get an answer, multiply across the bottom, get an answer, and divide the two. You can probably already see that we're not really going to need to worry too much about division, but we'll do good form and practice by making sure we include all of that. Ms. Laporte's going to do the math, so hopefully you are doing the math right now as well, if you haven't already. And when you multiply those, we should end up with 533.76 newtons. Remember, newton is the unit we have left. Pounds is gone, right? And then on the bottom, 1 times 1 with no units will just be a single 1. Therefore, our answer that we would be writing or circling or boxing at the end of everything would be 533.76 newtons. And I'm going to go right ahead and circle that because that is our answer. So someone weighing 120 pounds, that weight would be considered 533.76 newtons. Right, so being able to move between those units is very important. And so sometimes we'll have to go from the English to the metric, like we did here. And other times we're going to have to go from the metric into the English. Now I'm going to type or write this out, but I'm going to let Ms. Case explain this one. So you're hearing both of our voices, because sometimes, more than often, she does a little bit better than I do.
I don't know if I'd go that far, Ms. Laporte. All right, so if a truck weighs 9,000 newtons, how many pounds is that? Okay, so just like Ms. Laporte is doing, circling that 9,000 newtons, we're trying to get into pounds. All right, so our conversion factor is there on the left. Remember, we're always going to start with the number that is given in our problem. Okay, so we are starting with that 9,000 newtons as our numerator. Okay, and then we need to put that and make that into a fraction. So we're going to put that over the number 1. All right, and in order to get from newtons to pounds, we need that conversion factor. So if we have newtons as our numerator, that means that 4.448 newtons needs to be our denominator in our next fraction, leaving us with that 1 pound as our numerator. What gets crossed out here for our units is our newtons. So that gets crossed out. We are left with pounds. So circle that. That is what is going to be our unit ending. Then we need to do some math. So we've got 9,000 times 1. So we've got 9,000 pounds on top. 1 times 4.448 on the bottom. Remember, no unit there. We've crossed that out already. All right, and now we need to do some math. 9,000 divided by 4.448, and you should get 2,023.38 pounds. All right, and making sure you circle that answer will help us identify where your work is at and where your answer is, how you got there. To move or not to move. All right, here we are talking about net force. Okay, the motion of an object depends on the sum of all the forces acting on that object. Right, that is what is called that net force. So the sum of all forces acting on the object. Make sure you have that highlighted. Okay, so if the forces are in the same direction, you're going to add those forces together. Okay, think about when you would be pushing on something, right? That object's going to move in that direction.
All right, so Ms. Case just said that forces in the same direction, we are going to add the forces together and the object will move in that direction, okay? So if we are looking at something that is, whenever we draw these, I know we're going to be like a stellar, pictorial situation here, but Miss Laporte always uses boxes because it's easier to see. All right, so here's our object, whatever you want to call it. It could be anything. Your artistic abilities are probably better than mine, so feel free to draw something nice. So if we have this moving box that we're trying to move, all right, maybe you are going to be pushing on it, right, to the right, and maybe you are pushing on it with a force of 5 newtons. Okay, and then maybe your friend, because that's really nice of your friend, is also going to come over and help you. And they're also going to push on that same box in the same direction with 6 newtons of force. Okay. So if you're both pushing on the same box in the same direction, you are going to add the forces together. So when we try and figure out what the net force acting on this object is, we would say that that total net force is, adding them together, that's going to leave us with a net force of 11 newtons. All right. And that would be true whatever the direction is. So maybe both the forces were going to the left, or both the forces were pushing down, or both the forces were pushing up. As long as the forces, the arrows, are going in the same direction, you will add those forces together. All right. And then obviously the object will move in the same direction in which those objects are, or which those forces are being pushed.
Goes to the same if you're pushing that object and your friend is pulling it. So you might be on opposite sides of the object, but going in the same direction. All right, so make sure you make note of that as well. They don't necessarily have to be on the same side of the object, but if you're pushing and your friend is pulling, or vice versa, okay, that is going to show you that they're both moving in that same direction. So you will add those together still.
Cool. So here's that same scenario, but this time one of you is pulling right to the left, the other is pushing to the left. Always pay attention to which direction the arrows are going. That is going to tell you what you do in terms of directions here. So again, we would add those two forces together, all right? And that would be another 11 newtons of force, this time though, to the left, all right? Instead of to the right like that one. Good. All right, here you go, Case.
All right, so then if we have our objects going in different directions, we're going to subtract them. So that means that the objects move in the direction of that larger force. So whichever direction that heavier or that stronger force is the way that that object is going to move. Highlight
that, all right, in your notes before we jump back to the examples. All right, the object's going to move in the direction of the larger force. All right, so whichever side or direction ends up with the larger amount left over, that's the way in which your object is going to move. We often talk about it like tug of war. All right. Alrighty, so let's get another stellar drawing here for our second example with different directions. This time, our mathematical operation is going to be to subtract. So here's our object. Okay. Now this maybe you and your sibling, not now, of course, but back in the day when you were really young, are fighting over some type of, toy situation. Okay. And one of you is pulling on that toy will make you young. So only 3 newtons of force, right? And then your sibling, give them red because they're naughty, is pulling in the other direction, will let you win. And they're only going to pull with 2 newtons force. Okay. So we can see these 2 arrows are going in different directions. No longer are we on the same team here, pushing in the same direction or pushing and pulling in the same direction. Our arrows are going in opposite directions. So this means we have to subtract those 2 forces. All right. Something that you want to pay attention to, though, is which of these forces was bigger to begin with. Well, 3 is bigger than 2. So this force that is going to the left is going to win out. All right. So the object is going to move to the left, but we have to subtract these 2 forces to figure out how it's going to move. And it's going to move with only a force of 1 Newton to the left. And I should probably add that in here to be good about myself here. This one will be to the right. I can add that one. Okay. So we have 3 newtons to the left, 2 newtons to the right. And when we subtract them, you are going to have a net force of 1 Newton, and the object is going to move to the left. All right, so this would be like your tug of war example. Anything I'm missing there, Case?
Nope, I don't think so.
Okay, perfect. All right, take it away with John in the fridge there, Case.
All right, so John is trying to move a refrigerator. He is pushing with a force of 180 newtons to the left. Friction is resisting with a force of 45 newtons to the right. What is the net force on the refrigerator? All right, so first thing that we should do is probably underline the important things we have here. Okay, so we've got a force to the left of 180 newtons, and we've got a force of 45 newtons to the right. All right, and we always say draw a picture. So let's draw a fake refrigerator here. All right.
Make it a rectangle this time, so it's sort of refrigerator-esque.
Beautiful. All right, so we've got John pushing with a force of 180 newtons. So we're going to pick one side and we're going to say we've got force going to the left with 180 newtons. All right, but we've got friction resisting that force with 45 newtons, and that's going to the right. All right, so now are they going in the same direction or are they going in opposite directions? Okay, hopefully you said they are going in opposite or different directions. Okay, so that means that we need to do what? Add or subtract? Good, we will need to subtract. So you will take your 180 newtons and subtract 45 newtons from that. You should have gotten 135 newtons. Now we're not just done quite yet, right? We need to figure out which way is this net force going. Is it going to the right or is it going to the left? So in order to figure that out, again, up there on that green Post-it, it says that it will move in the direction of the stronger force. So the stronger force is your 180 newtons, so it is going to move to the left. Okay, so you can either write the word left or you can draw that arrow. Right, so John has his friend Ryan come to help him move the pool table. John is pushing with a force of 120 newtons to the left, and Ryan is pushing with a force of 115 newtons of force to the left. Friction is resisting with a force of 120 newtons to the right. What is the net force on the pool table? All right, so underline the information that we have here first. So we've got one force of 120 newtons to the left, another force of 115 newtons to the left, and then we also have a friction resisting with 120 newtons force to the right. We're trying to find that net force again. All right, so let's mark those up on our picture that we're going to draw here. All right, so we've got 120 newtons to the left. Then we have another 115 newtons to the left. And then we have a resisting force of 120 newtons to the right. And what you'll notice here, what Ms. Laporte did was she made those ones pushing to the left the same color. All right, so in order to solve this, we should first start with the forces that are moving together. Let's add those up first because they are the same direction. So you'll take the 120 newtons and the 115 newtons, and because they are going in the same direction, please add those together. We've got 120 plus 115, which should get you a total of 235, newtons. So that's our total number of our force on that right side of our pool table, okay? That is still pushing to the left. All right, and then we have our total newtons pushing to the right of 120 newtons. So since these are going in opposite directions, right? One's going to the left and one's going to the right. They're pushing against each other. These forces are different. So we need to subtract those two numbers from one another. So you'll take 235 newtons minus 120 newtons, and you should come up with 115 newtons. All right, now we need to figure out which direction it will move, and it's going to move in the direction of the stronger force, which is to the left. All right, so your complete answer for that is 115 newtons to the left. Okay, and again, that's because you have those two people on that one side pushing to the left on that one. Make sure that you are doing that part first.
Yes, always do any adding together first before you subtract forces going in different directions. All right, last thing to go over here before we wrap up.
All right, so are they balanced or unbalanced forces? When we're talking about balanced forces, these are when their net force is equal to 0. All right, so this will mean that the object is at an equilibrium. That means that they're just kind of holding out right where they're at. They're not moving at all. Their motion doesn't change. So if you get something that comes out to a 0 net force, that means that it's balanced. It's at equilibrium. And when we have our net forces acting on an object that are unbalanced, that's those examples that we just did. So the net force is not 0. That means that the object is going to move. It's going to have some kind of motion or change in motion.
So just so you have some examples in your notes for that, right? Down here, if I can put a little something on this. So if I do my little box, right? Something that is pulling my object this way, and I have something else pulling my object in the opposite direction. And let's say that each side is pulling with an equal amount of force. All right, so I'm pulling with 5 newtons on either side. Those are going in opposite directions, and I'm going to subtract my 2. So the overall net force acting on this object is going to be 0. Therefore, whatever this object was already doing, so if it was already in motion, like in space, it's going to keep moving. If it is sitting at rest, it's going to stay at rest. All right, that is the definition of inertia. So as long as the forces are balanced on either side, top or bottom, left or right, for our examples, if they are balanced, then you have a net force of 0, then the object's motion doesn't change. All right, we consider that to be balanced forces. And as Newton's first law said, objects are not going to change their motion when balanced forces are acting upon them, only when unbalanced forces are. So all those other examples that we have done today, all those other pictures we have drawn have shown you examples of unbalanced forces where we have some type of force. Let's do one this way. We haven't done something like this. We have a force acting in one direction here, and maybe we'll do a someone. So we have 2 forces. So we're pushing it up and we're pulling it up. All right, and so we have 2 forces acting on an object, 4 newtons. Let's say up there, and let's say 3 newtons down here, okay? Because these forces are not balanced, all right, we have 7 total newtons of force going up the object's motion is going to change. All right, its inertia is going to be overcome, and it is going to change its motion. And as we head into the other Newton's laws, we'll see how the mass of that object, along with the amount of force applied, is going to determine how fast that change in motion is going to occur.